Astronomy comes from the Greek word astronomia, which means law of the stars. Unlike other fields of science, astronomers are unable to observe a system entirely from birth to death because the lifetime of stars and galaxies spans from millions to billions of years. Instead, they must rely on snapshots of bodies in various stages of their evolution to determine how they formed, evolved, and died. There are various ways to obtain information about celestial objects, the most important of which is the light they emit. Before we examine the properties of the light emitted by cosmic sources, let's see other sources of information available to the astronomer.
In addition to light, astronomers study the contents of the universe using cosmic rays and other elementary particles, like neutrinos emitted by supernova explosions. Gravitational waves is the new way to explore the universe. There are ripples in space-time caused by some of the most violent and energetic processes in the universe. The strongest gravitational waves are produced by cataclysmic events such as colliding black holes and neutron stars, supernova, and possibly even the remnants of the Big Bang. Information about the solar system comes from meteorites. A meteorite is a fragment of rock or iron from outer space, which survives passage through the atmosphere and impacts the surface of the Earth. While these are very useful sources of information, they represent a very tiny fraction of the amount of data collected by the astronomer. It is believed that as much as 99% of the information is received as light. Light is the primary source of our knowledge of the cosmos.
Astronomers prefer to use the term electromagnetic radiation instead of light because most of us think of light as just what we can see with our eyes. Electromagnetic waves, like any wave, are described by the wavelength or by the frequency. The meaning of these quantities is easily understood in a graph. The intensity of waves may be represented as a function of time or distance. From the distance graph, we can determine the wavelength, which is the distance between two consecutive crests. From the time graph, we can determine the period, which is the time needed for the wave to cover one wavelength. The frequency is simply the inverse of the period. Wavelength and frequency are related through the speed of light, which is the speed at which light moves in space. Frequency is a measure of the number of wave crests that pass a fixed point per second. At higher frequencies, more crests will pass the point each second, which implies that the wavelength must be short. As frequency decreases, fewer waves will pass and the wavelength will be longer. Electromagnetic waves also carry energy. The larger the frequency, the more energetic is the radiation.
The spectrum of electromagnetic radiation is a range of all types of light. Depending on the wavelength or frequency or energy of the electromagnetic radiation, we classify it into different bands. These are called radio, microwave, infrared, visible or optical, ultraviolet, X-rays, and gamma rays. Although there are no precisely defined boundaries between the bands, this classification goes in the decreasing order of wavelength or increasing order of frequency or energy. You are more familiarized with the electromagnetic spectrum than you may think. Your radio captures radio waves emitted by radio stations, bringing your favorite music. Radio waves are also emitted by stars and gases in space. Microwave radiation will heat up your food in just a few seconds or minutes, but is also used by astronomers to learn about the structures of nearby galaxies or the universe. Night vision goggles pick up the infrared light resulting by thermal radiation emitted by our skin and other objects with heat. In space, infrared light helps us map the dust between the stars. Visible light is electromagnetic radiation that can be perceived by the human eye. It covers a very small portion of the entire spectrum. The main source of light on Earth is the sun. Sunlight allows the plant to perform the photosynthesis and provides virtually all the energy used by living things. Our eyes have adapted to see at the typical wavelengths of the light emitted by the sun. Ultraviolet radiation is emitted by the sun and is the reason skin tans and burns. Hot objects in space emit UV radiation as well. A dentist uses X-rays to image your teeth, and airport security uses them to see through your bag. Very hot gases in the universe also emit X-rays. Doctors use gamma-ray imaging to see inside your body. In the universe, gamma rays are produced by several highly energetic processes, involving black holes, pulsars, and interaction of cosmic rays with interstellar gas.
By measuring the radiation that the stars emit, astronomers can determine how bright they are. The measurement of the brightness of celestial objects is called photometry. Photometric measurements provide fundamental information about the nature of the object. They tell us about its luminosity, distance, or chemical composition. Photometry is also used to study the light variations of objects. These variations allow astronomers to detect extrasolar planets, determine orbital periods, or find the radii of stars in an eclipsing binary.
It is believed that the greatest astronomer of antiquity, Hipparchus, was the first to classify the stars visible to the naked eye. According to their brightness, they were classified into 6 different categories, or magnitudes. The brightest stars were assigned to Category 1, and the faintest stars visible by the human eye to Category 6. In 1856, the English astronomer Norman Pogson formalized the system by defining a typical first magnitude star being 100 times as bright as the typical 6th magnitude star. In other words, an object that is measured to be 5 magnitudes higher than another object is 100 times dimmer. This system of magnitudes is still in use today. In the magnitude scale, higher numbers correspond to fainter objects, lower numbers to brighter objects. The very bright objects have negative magnitudes. Magnitude 6 is considered to be the limit of human visual perception. Note that this is the apparent brightness and not the real amount of energy emitted. The Sun appears as a very bright object because it is close to us. Galaxies which contain billions of stars like our Sun look faint because they lie far away from us.
For many centuries, the only way for people to learn about the stars and the planets was with their naked eyes, and it was with the eyes alone that the modern constellations were conceived and the first 5 of our planets were revealed. With the advent of optical telescopes, it was possible to gather more light and reveal more detail that can be seen with the naked eye.
Astronomers use telescopes to see distant objects. In fact, the word telescope comes from the Greek language and it means far-seeing. Telescopes work by using lenses, curved mirrors, or a combination of both, to gather and focus light from the night sky, usually to build an image. Although the inventor of a telescope is still unknown, Galileo is considered to be the father of observational astronomy. He was the first person to use a telescope to observe celestial objects in 1609. Until then, magnification instruments had never been used for this purpose. A telescope is simply a light-gathering device. Its power is given by the amount of light it can collect. Acting as a light bucket, it collects all the photons that come down on it from a faraway object. A larger bucket catches more photons, resulting in more received light in a given time period, effectively brightening the image. In order to observe dim and faraway objects, telescopes have really big mirrors or lenses.
because light moves at a fixed velocity, the light coming from a distant galaxy takes longer time than a nearby star. Therefore, looking at distant objects means looking back in time into older objects. This is the reason that astronomers measure distances in terms of the time that light needs to travel from one point to another. A light year is the distance traveled by the light in 1 year. Because the speed of light is 300,000 km per second, 1 light year is equivalent to more than 9,000 billion kilometers.
There are two main types of telescopes, refracting and reflecting. The main difference is that in refracting telescopes, light goes through lenses, while in reflecting telescopes, light is reflected by mirrors. In a refracting telescope, light enters through the main objective lens at one end. The lens refracts or bends the light to a point of focus. This is then magnified by the eyepiece to form an image at the other end. Refracting telescopes were the most common type of telescopes in use before the early 1900s. The largest refractor ever built is the Yerkes telescope, located in Williams Bay, Wisconsin, and run by the University of Chicago. It has a 1 meter diameter lens, mounted in an 18 meter steel tube, and is housed by a 27 meters diameter steel dome. The main problem with powerful refracting telescopes is that their lenses are large and bulky. Large lenses are also heavy and tend to sag under their own weight, deteriorating the image quality as the lenses distort. Moreover, the long mounting tubes are hard to make mechanically stiff, and so they tend to flex under the weight of the lens, making it hard to keep the optics aligned. These problems became more important as telescopes grew increasingly larger. That is the reason why astronomers left lenses behind and shifted to mirrors. Mirrors can be built much larger and thinner than lenses, which means reflecting telescopes are far more powerful while keeping weight under control. In a reflecting telescope, light enters at one end and is reflected by a concave-shaped primary mirror at the other end, towards a smaller mirror known as a secondary mirror. The mirror reflects light into the eyepiece, which is usually mounted on the side of the telescope. Isaac Newton used a flat secondary mirror at a 45-degree angle to reflect the light to an eyepiece at the side of the telescope tube near the top. Such an arrangement, called the Newtonian design, is used by many amateur telescopes. Many reflector telescopes use another light path called the Cassegrain design to reflect the light back through a hole in the primary mirror, so that detectors or the eyepiece can be conveniently placed at the focal point behind the telescope. Most of the large telescopes used for research, including the Hubble Space Telescope, are of this design. The largest monolithic primary mirror in the world is installed on the Subaru telescope in Hawaii with a diameter of 8.2 meters.
Objects in the night sky appear to move over time. Just as the sun rises and sets during the course of the day, celestial objects such as the moon, planets, and stars change position during the night. Astronomical targets appear to move across the sky in an arc from east to west. This does not mean that the stars are actually moving. The apparent motion of the stars is caused by the rotation of the Earth, which makes the whole sky seem like it is actually rotating.
To be able to measure the brightness of a star, it must remain fixed in the field of view for a certain amount of time. Without constant correction, objects will rapidly swing out of view. Thus, the telescope must rotate in the same direction to follow the stars. The most efficient way to do this is to use an equatorial mount. In this mount, one of its axes is always parallel to the rotation axis of the Earth, called the polar axis. It is pointing to the north or south celestial pole depending on which hemisphere the telescope is located. Motion about the polar axis allows the telescope to rotate in an east to west arc following the celestial objects. The other axis, called the declination axis, is perpendicular to the Earth rotation axis to allow the telescope to move in a north-south arc. The advantage of an equatorial mount lies in its ability to allow the telescope to keep stars fixed on the field of view. This is done by driving the polar axis at a constant speed using a sidereal or clock drive.
Astronomers don't observe with their own eyes like Galileo did when the telescope was invented. In order to record what he saw, even Galileo used to make notes and drawings of the things he saw with his eyes through the lenses of his telescope. Photography was quickly adopted as a convenient means of recording data, and astronomers began to use it as soon as it was invented. Later on, digital cameras revolutionized the way astronomers collect and store data.
The first photographs of sky objects date back to the beginning of the 19th century, like these ones of the Sun and the Moon taken in 1845 and 1839. The innovation of dry plate photography in 1871 helped astrophotography become a serious research tool. This way, astronomy entered the era of deep sky exploration, by allowing astronomers to take photos of deep space, like the first photo of a nebula. The advent of digital cameras in the 1970s revolutionized astronomy. They were the primary data recording medium in modern astronomy. Digital images have replaced film and photographic plates for professional astronomical imaging. This is largely due to the fact that digital cameras are more efficient at collecting light than photographic film and produce an astronomical image in a matter of seconds to minutes rather than hours, and the data can be easily processed. Digital cameras use a CCD chip, which stands for Charged Coupled Device. The CCD chip plays a similar role to the film of a traditional camera. A CCD sensor has to perform 4 tasks to generate an image. The first task is to generate charge. The basic principle of a CCD sensor is that it is made up of a material that generates an electric charge when illuminated. The brighter the illumination, the greater the charge. It is possible to estimate the amount of light that has fallen onto the camera by examining the amount of charge it has stored up. The second step is to collect the charge. The light-sensitive phase is rectangular in shape and is subdivided into a grid of discrete rectangular areas called pixels. The pixels act like buckets that collect the charge generated by the light impacting the chip. There are millions of pixels in a camera. Transferring the charge is the third task. The charge is transferred from pixel to pixel towards one side of the chip where it is read out. The amount of charge in each pixel of a row is registered one row at a time. And the final step is to create a picture. The charge which has accumulated in each pixel is amplified and converted into a number. This value is sent to the computer and the process repeats until the content of each pixel is read out and displayed as an image on the computer screen.
A telescope works like the human eye. Both the eye and the telescope produce an image by focusing light onto an array of light sensors. However, telescopes are much better at peering into the distant universe than the human eye. But how are they able to see such faint and distant objects, and why is it that our eyes cannot?
In the human eye, light goes through the cornea. Behind is the iris, the color part of the eye, and the dark hole in the middle is called the pupil. In a telescope, the primary mirror is the equivalent to the pupil, with the only difference being that the pupil can widen or narrow depending on the intensity of the light, while the size of the primary mirror is fixed. In the eye, directly behind the pupil sits the lens, which focuses light towards the back of the eye, where the retina is located. The retina functions much like the film in a camera. It is the light-sensitive part of the eye which transforms light intensity to electric signals transmitted to the brain. In a telescope, the light is focused by the secondary mirror. Then it is recorded by a digital camera which is located at the focal point of the telescope. To get a better understanding of the capabilities of the human eye and of a telescope, let's compare some key performance characteristics. A camera installed in a telescope has a shutter which can open and close. When we want to measure the light coming from a star, we open the shutter for a certain amount of time, known as the exposure time. The exposure time determines how light or dark an image will appear. Bright objects require short exposures of a few seconds, while faint objects may require very long exposures of minutes or even hours. Although the pupil is an adjustable opening that controls the intensity of light permitted to pass through the lens, the human eye does not have a shutter. In contrast, it sends an image to the brain 15 times a second. This is equivalent to a fixed exposure time of roughly 1/15 of a second. The possibility to have long exposure times allows the camera to gather more light, hence it can detect much fainter objects than the human eye. For example, for a 30-minute exposure, the telescope can gather light for a duration 27,000 times longer than the human eye to make a single image. The light-gathering power of a telescope is the amount of light it can collect. The larger the surface of the mirror, the more light it gathers. In the eye, the aperture is the pupil. Unlike the telescope, the pupil changes in size depending on light conditions. However, the change is very slight and not enough to allow us to see very faint objects, even at the maximum size of the pupil. The gathering power is proportional to the square of the diameter of the aperture, which in turn is proportional to its area. So, for example, the human eye has a pupil diameter of about 7 millimeters. Comparing it with a 1-meter diameter telescope, we find that the telescope has more than 20,000 times larger collecting power than the eye. Combining the exposure time and light gathering power, we conclude that in half an hour, a 1-meter telescope collects 540 million times more light than the human eye. The area of a sky that can be seen by an optical system is called the field of view. Having a large field of view is a survival advantage for humans because we quickly react to dangers such as animal predators or moving cars. In contrast, telescopes are designed to focus on just a small part of the sky. The eye allows simultaneous visual perception of an area of about 160 by 175 degrees. In a telescope, the field of view depends on the characteristics of optical elements like mirrors, lenses, or size of the CCD camera. In general, the field of view of a telescope is less than 1 degree. While the human eye can perceive color, the images recorded with a telescope are typically black and white. This is because the camera CCD only records the brightness of the light falling onto it. To create a color image with a telescope, we need to combine images taken with different color filters. However, in many cases, these are not the true colors of the observed object. Resolving power is the ability of a telescope to distinguish clearly between two objects that lie close together in the sky. It also depends on the size of the primary mirror. The larger the surface of the mirror, the finer detail it resolves. An important application of the angular resolution is in the observation of visual binary stars or the study of stellar clusters, where millions of stars are located in a relatively small volume of space. The angular resolution of the human eye is approximately 1 arcminute, which corresponds to being able to separate two objects that are 30 centimeters apart from a distance of 1 kilometer. On the other hand, a 1-meter telescope can separate the same objects from a distance of 60 kilometers.
Astronomers face a formidable obstacle before they can detect light: the atmosphere. The atmosphere affects astronomical observations in two ways. First, it prevents some types of electromagnetic radiation from reaching the surface of the Earth where telescopes are located. Second, it distorts the image of the celestial objects, affecting the quality of the astronomical observations.
As the light waves pass through the atmosphere, they interact with the molecules and particles present in it. Light is scattered, reflected, or absorbed by the atmosphere, allowing only small portions of the electromagnetic spectrum to go through. It is in these small portions or windows where light penetrates the atmosphere that the astronomer places telescopes. The optical and radio wave bands are two major windows for ground-based observing. If astronomers want to study light at other wavelengths, for example X-rays or gamma rays, and some infrared bands, they have to use satellites with appropriate detectors outside the atmosphere. When light enters the atmosphere, the different temperature layers and wind speeds change the direction of the light waves, leading to distortions in the image of a star. The air is constantly in turbulent motion, and light from celestial objects is bent randomly in many ways over time periods of tens of milliseconds. The most obvious result of this effect is twinkling, where the brightness of a star seems to fluctuate. In astronomical terminology, this effect is referred to as seeing, which describes the clarity with which stars and other celestial objects can be observed. The most common way of describing seeing is by measuring the width of a star on the focal plane. The star is seen at the focal plane as a disk. The diameter of the seeing disk is a measure of the astronomical seeing conditions. This diameter is measured in arcseconds. The lower the number, the better. Good seeing is when the air is stable and the twinkling is small. Details as small as 0.5 arcseconds can be seen when the seeing is good. Poor seeing happens when the air is turbulent, so the images dance about and details smaller than 2 to 3 arcseconds cannot be seen. Because turbulence in the atmosphere is the main factor affecting the quality of the astronomical observations, the less atmosphere the light crosses, the best picture of the cosmic sources are obtained. The site for an astronomical observatory must have the following characteristics. It should be at a high altitude because it minimizes the light loss by the atmosphere. It should be dry because it maximizes the sky transmission. It should be dark because it minimizes the sky brightness. It should be clear because it maximizes sky throughput. It must have low wind speed and turbulence. It must have minimal snow load. These characteristics are more easily found on the top of mountains because the higher up in altitude, the less atmosphere to see through. Therefore, this is the reason professional observatories are usually located at high altitudes. Since the atmosphere is the main reason affecting the size of the seeing disk, one way to reduce the twinkling is to put the telescope above the atmosphere. The Hubble Space Telescope is orbiting the Earth at an altitude of 550 kilometers. It has recorded some of the most detailed images in the visible, ultraviolet and infrared light, allowing a sharp view of deep space. However, it is extremely costly and technologically challenging to send large telescopes into space. So telescopes with diameter larger than 5 meters have to be deployed on Earth's surface. But this poses many challenges. The weight of the mirror itself and external factors such as wind or temperature variations changes the shape of the mirror during observations, degrading the quality of the images. One technique that astronomers and engineers develop to increase the quality of images taken by large telescopes is known as active optics. The idea behind it is that the mirror is supported by an array of actuators. These are pistons that move very accurately and can be controlled precisely. By pushing the mirror, they correct its shape and compensate for the distortion produced by gravity. The corrections applied by the actuators are calculated in real time thanks to a computer with an image analyzer that detects even the smallest deviations from the ideal mirror shape. Although active optics can ensure that a telescope's main mirror always retains a perfect shape, the turbulence of the Earth's atmosphere distorts images obtained at even the best sites in the world for astronomy. The solution is adaptive optics. An adaptive optics system tries to correct the distortions introduced by the Earth's atmosphere. The difference between active and adaptive optics is that active optics act on the telescope's primary mirror, while adaptive optics corrects the distortions in the light path using computer software and a small deformable mirror. Adaptive optics requires a fairly bright reference star that is very close to the object under study. This reference star is used to measure the blaring caused by the local atmosphere so that the deformable mirror can correct it. Since suitable stars are not available everywhere in the night sky, astronomers can create artificial stars instead by shining a powerful laser beam into the Earth's upper atmosphere. Thanks to these laser guide stars, almost the entire sky can now be observed with adaptive optics.